Okay, so this is the beginning of the equilibrium chapter. We're just going to do the first two sections, so this one's pretty short. So what is equilibrium? Because I mentioned that in the last lecture, and that's that some reactions can go forward and backward, and at some point they reach what's called an equilibrium. This is called a dynamic equilibrium. Dynamic meaning it's constantly moving. So what happens at equilibrium for a reversible reaction is when both the reactants and the products reach what's called a steady state. Okay, so that's what I'm gonna define this as. Both R and P reactants and products reach what's called a steady state. And actually what that means is the concentrations of the forward and the reverse reactions stop changing, but the reactions are still happening. So you're still having forward reactions, you're still having reverse reactions. It's just that they've steadied out and now the concentrations have stopped changing. So forward and reverse reactions happen, but concentrations are constant. Okay, that's when you know you've reached equilibrium. So at equilibrium, the forward and the reverse are still happening, but the reason that the concentrations don't change is because at equilibrium, the rate of the forward equals the rate of the reverse. And I talked about this in the last video. If you're at equilibrium, the rates are exactly the same. And you can kind of see that for this reaction in this graph. They change how fast they're happening until they steady out and they're actually at the same rate, not necessarily the same concentration, but they're at the same rate, maybe different concentrations. So the concentrations stop changing. So an analogy for this is like a tug of war, right? At some point, you're both pulling still, but it's not moving because you are at equilibrium. So we might be over here, we might be over here. Forward and reverse reactions are happening, just not changing because you're at equilibrium, okay? Now, again, that does not mean that the concentrations are the same. Tug of war analogy, that doesn't mean that one team isn't stronger than the other. One probably is stronger. It's just that it's not moving anymore. So not the same concentrations, just the same rate, okay? They can all have different concentrations. So I have a little simulation here that I want to share with you. Okay, so this is a simulation. What I'm going to do is I'm going to put, I don't know, like 50 A's into a reaction and see what happens. Okay, oh, no, that's not what I meant to do. 50. And essentially they're all colliding and colliding and colliding, and sometimes they're going to turn into products. It's kind of like it gets over the activation energy, and now I'm getting products over here. Okay, if the activation energy is lower, which I don't think it'll let me change it right now, then that will happen easier. If the activation energy is really high, then it's more difficult to turn into products. So they're constantly going back and forth and back and forth and back and forth. Okay, if you change the temperature, cause more collisions, and you might cause them to react more or go more toward the products. Okay, if I throw a bunch more in there, they're going to react, and then, oops, 700. And then they're eventually going to reach equilibrium again, but everything is still always moving. They're still colliding. They're still making products. It's just that at some point, the concentrations stop changing because the rate at which ones are turning into B is the same rate at which they're going back to turn into A. So if you want to play with this, you totally can. But if you change the activation energy, you can see what happens. You change the temperature, you can see what happens. They're eventually going to not even out concentration-wise, but they're going to be changing at the same rate, and I'm really not going to get much of a fluctuation in amounts. That's what equilibrium is. Okay, so essentially every reversible reaction has what's called an equilibrium constant, okay, and we're going to get into that. So we've been talking about rate constants, that K in my rate equation, and we said at equilibrium, the rate of the forward reaction equals the rate of the reverse reaction. So I'm going to show that again now. Kf times, this was the forward reaction in the example above, equals Kr times NO2 squared. Okay, so if I'm going to try to get a ratio of these, Kf to Kr equals the concentration of NO2 squared over N2O4. Okay, and what this is called when I am getting a ratio of the rates is big K, which is the equilibrium constant. Okay, and each reaction that is reversible has an equilibrium constant. So when they're at equilibrium, it's actually a comparison of the concentrations. Okay, so equilibrium constant, every reversible reaction has one. Reaction has, and I'm just going to write K. Has a K. K does change with temperature though, so keep that in mind. K changes with temp because right, if it's higher temperature, you can cause more collisions to happen essentially. So K changes with temperature, just kind of keep that in mind. But how do I actually calculate K? What does big K or the equilibrium constant mean? So if I were to write a generic reaction, so I like doing AA plus BB makes CC plus DD. Oh, and by the way, the reversible reaction arrow is a half arrow to the right, half arrow to the left. Please don't do a double-headed arrow. That's not technically the same thing. That means something else. So just kind of keep that in mind. So if I'm going to write the equilibrium reaction based on the concentrations for this, remember it's a comparison of the forward and the reverse. So K is actually equal to the products, which are C to the power little c times D to the power little d over A to the power little a over B to the power little b. This is the generic form of K. We can actually calculate K if we have all of the concentrations. Okay, this is like one of the only times I will tell you this. There are no units on K. All right, these stand for molarity, right? But they're all going to cancel out, at least for the most part. So there's no units on K, the equilibrium constant. Okay. All those concentrations cancel out. So if I said, write the Kc expression for this equation, what you would do is you would write Kc, now C stands for concentration, and I'll talk about that in a minute, is products, remember? So CH4 times the concentration of H2O over the reactants, CO, times the concentration of H2, and it should be to the power of any of their coefficients. So this is how you write the K equation for this specific reaction. Okay, now there's also Kp. So notice I pointed out that C earlier. C stands for concentration. P stands for pressure. Okay, so you can actually calculate a K value based on either pressures or concentration. So if we're using gases, pressures can be really useful, right? So the way that Kp is written then, so we said Kc, it looks like this, right? It's concentration A times, oh shoot, did that backwards, didn't I? It's products over reactants. Silly. C to D over A to B. Pressures are similar, except you're just going to use partial pressures. So it's the partial pressure of C to the C power times the partial pressure of D to the D power over the partial pressure of A to the A power times the partial pressure of B to the B power. So it's just the same. You're just going to use partial pressures, and you can calculate this as well. Now, Kp and Kc are not necessarily exactly the same number. They have a relationship, and this is the equation you will have to be able to use, and that is Kp equals Kc times RT, there's that gas constant, to the delta N power. Now, R in this case, you do have to use the 0.08206 number because Kc is in concentration, it's molarity, so moles per liter. And this has liters and moles in it. So the only way to get this one to work is use the correct R. And then I got to tell you what delta N is. Delta means change in, right, moles. And this is actually the moles of gas. Not a gas, moles of gas in the products minus the moles of gas in the reactants. Okay, so products minus reactants, like most change in equations are, but it's the number of moles in the balanced reaction. So we're going to do one of these in a little bit, but what that means is how many moles of gas are produced versus how many moles of gas are in the reactants. Okay. So what does the K value mean? And we're going to get more into this in the next lecture. But if K is really, really big, if you look at the K equation, if it's really, really big, that would mean I have larger numbers on the top, right? So I would have a lot of reactants. So that, or sorry, a lot of products. So that would mean that the products are favored. Whereas if K is really, really small, that would mean I would have much bigger numbers on the bottom. So A and B would be favored. So the reactants are favored in that case. Okay. I've got pictures of that over here. Essentially, if it's really, really small, like 10 to the negative third or smaller, I have mostly reactants. If it's 10 to the third or bigger, it's mostly products. And anything in between, I have reactants and products present. Yes, technically anything over 1 favors the products. But if it's anything between 1,000 and 0.001, there's a significant amount of both reactants and products there. So you kind of have to keep that in mind. Okay, so last thing I want to talk about really before we do some examples are changes in K. So essentially, if you know the K value, so the equilibrium constant for a specific reaction, you actually know the K value for the reverse reaction, and it's actually the inverse. So if you reverse the reaction, you get inverse of K. So that would mean like 1 over K. Right? So the K of this equation, which is the reverse of this one, is 1 over 0.212 and whatever that is. Okay. Now, if you multiply by a factor, so notice this is doubled from the first example, you are actually going to take the K value to that power. So power of whatever factor you multiplied by. So essentially, this was times 2. You're going to take the K value that we know, and you're going to square it. Okay. And then when you add reactions together, you don't add K values, you multiply the K values. Multiply. Okay. So if I'm adding these reactions together to get this overall reaction, I'm not adding my K values, I'm going to multiply that times 7.2 and whatever that is. I think it's 0.1008. Okay. So essentially, this is kind of like Hess's law, right? Where you have to like piece the reactions together to get the overall reaction. But in Hess's law, like whatever you did to the reactant or to the reaction, you also do to the delta H. And this one, whatever you do to the equation, you actually like take it one step further, right? So if you flip it, you do the inverse. If you multiply it, instead of multiplying it, you're going to take it to that power. And when you add them, instead of adding them, you're going to multiply them. So it's kind of like one step further. Okay, so K, you can actually find the equilibrium constant of a new reaction based on these, but it's not like adding Hess's law. You have to take the K values one step further. Okay. A couple of other vocabulary terms or different types of equilibrium. You can have a homogeneous equilibrium or a heterogeneous equilibrium. You can probably figure out that what that means, right? Homo would mean they're the same. So substances are all in the same phase. So reactants and products, substances in same phase, meaning like gas or aqueous or whatever. And if it's heterogeneous, substances in different phases. So that would be like if I have gases and liquids in my reactants, something like that. Okay. Now there is an important thing to remember about, especially things that are heterogeneous equilibriums. When I write a K equation, so my big K equilibrium constant equation for a reaction, we actually leave out liquids and solids. Leave L and S out of K equations. This is super important. Now, why do we do that? Technically, solids and liquids in a reaction aren't going to affect the equilibrium because there's so much of them there. There's actually not a concentration of a solid. It's just the solid. There's not a concentration of a liquid, just a liquid. Only aqueous and gaseous things should be involved. So if you look here at my example, this reaction here, I'm doing it in a bell jar, right? I've got CO2 as a gas. And my CaO and CaCO3 are both solids. So really, no matter how much solid I have in there, the equilibrium is only based on the CO2. So essentially, these guys, because they're solids, should not be in my K equation. So I would write the K equation is, remember, its product. So CO2, and I leave this guy out to, it doesn't have a coefficient, so no power. And I would leave this out. So it's really just based on the CO2 concentration. Okay, so solids and liquids are left out of the K equations. So now that we've talked about all of that, we've got example 2, 3, and 4 here. I want you to try these and then check back to check your answers. So pause. Okay, so I'm going to walk through these really quick, so check your answers. So A should have been the inverse because it's the reverse reaction, 0.0833. B should have been squared because it was doubled the reaction, so 144. And C was halved. Oh, sorry, that should be to the 1/2 power. Okay, and inversed. So if I inversed it, okay, so I reverted it, so I did 1 over, and I took it to the 1/2 power, which is really just the square root, I get 0.289. So it doesn't matter what order you do those in, you should get the same answer either way. All right, example number 3, I use that Kp equals Kc times RT to the delta N equation. So I put in my Kc value, gas constant, temperature, and then my delta N, remember, is the number of gas moles in the product. So 2, got 2 NOBRs, minus those in the reactant. So there's 2 NOs and 1 Br2 here. So this is 3 moles. So it's 2 minus 3. So it was -1. You usually get 1.58 times 10 to the -4. All right, and then writing our equations. Remember, solids and liquids are not included in our K equation, so I left those out. So you should have gotten these 2. Good luck.